So welcome to the Civil 989 seminar. Today we're going to have Gabby speak on a project that she's been working on. And I'll let her introduce the topic and go through the presentation. You may notice that at the bottom it doesn't say our seminar name. It says IHEAP Conference. So this is actually a practice run for Gabby when she goes next week to present this at a national convention. So without further ado, Gabby, you start.
All right. Thank you. Thank you guys for coming to my presentation. The topic I'm going to present today is the empirical side friction factors on circular horizontal curves at highway railway grade crossings. And like Dr. Rylett said, this was a project that I was doing this summer. So some of the things that I'm going to talk about today is I'm going to give you an introduction background on horizontal curves, super elevation, centripetal acceleration, as well as side friction. I'm also going to give you an objective and a scope on my research, my data collection, how I collected my data, where I collected my data, my results, and I'm going to finish off with some concluding remarks. So the first topic is on horizontal curves. So we know when a vehicle is going around a horizontal curve, what's keeping that vehicle on that curve is centripetal acceleration, which is, well, centripetal force, which acts towards the center of the curve. If you don't have that force, then your vehicle is just going to fly off of your curve. Another force that you have is your friction, which acts between your tire and your pavement. So basically, the higher your friction is, the higher your centripetal force is that's keeping your vehicle on that curve and going around the curve. This is also why you can go faster on dry pavements than you can on wet pavements. And you can also go faster on wet pavements than you can on icy pavements. This goes to the formula of your force is equal to your mass times acceleration, your acceleration being your velocity squared divided by your radius. So in this formula, your mass and your radius are constant. The only thing changing is your velocity, which is squared, and this is a function of friction. So the higher your friction is, the higher your velocity you have to maintain on that curve. So we have learned some time back that if you want to increase your centripetal acceleration, you're going to bank your curves. So you're going to super elevate them. When you super elevate your curves, now you have gravity, that's another force acting towards the center of your curve. For when you're designing curves, two things you want to think about when you're designing them to go around faster. Two things you're thinking of is your super elevation and your friction, and these two, they work together to give you your centripetal force. So over here on your right, you have the formula for friction. This comes from your green book. And the picture is a picture of a test site in Germany. Obviously, we do not design our roadways to be this high banked, but the picture more or less gives you the concept that you need your super elevation and your friction to get centripetal force to go around the curves faster. So your maximum side friction values from the Green Book, this was from 2004-2011, under wet conditions, you have higher friction values at low speeds and lower friction values at high speeds. And this is because of wet conditions. So comparing this to values from earlier in the Green Book, the values from 2004, well, 1995 to 2001, sorry, these had very little changes. The only major change was between 2001 2004, and like I said, 2004 and 2011, they're exactly the same. They did not change then. Based on your Green Book of 2011, maximum side friction factors that you can get under wet conditions for new tires is 0.5 at 20 miles per hour and 0.35 at 60 miles per hour. For smooth tires under also wet conditions, you can get 0.35 at 45 miles per hour. So like I said, these are maximum, these are not comfort. However, the study below that by Moyer and Berry, which was done in the 1940s, this was a comfort, also under wet conditions. So this is basically what the driver is feeling, not going maximum. You have your different ball bank readings going at different speeds to give you your different frictions. And as you can see here, your friction levels, your friction values do go down as your speeds increase. So Basically, my research question is, what are vehicles doing right now? What friction values are they using? We know that pavements have changed over time. The materials have changed as well. What I mean by evolution of vehicles, your tires are different than they were in the 30s. They're not 30s and 40s, they're not the same that you use now. Are we over-designing our highways? Are we under-designing them? What exactly are we designing for? So when I said, what are the drivers actually using right now? Are they going at your design limits? Are they going above it? Are they going under it? Where exactly do they lie? So my data collection was basically a trailer that was placed by the railway tracks. It consisted of 2 IP cameras. These cameras were to watch the vehicles as they went around the curves. There is an HD sensor which gave me the speed of the vehicle, how fast was the vehicle going around the curve. Solar panels were to charge batteries during the day in case you wanted to get some data at night. Then Wavetronics DVR and laptop that was placed inside the trailer where I could gather my data. Since I am living in Lincoln, in Nebraska, I gathered my sites close to Lincoln. Some of these were a little outside of Lincoln, but they were also of major concern to the Nebraska Department of Roads, which is why I chose to do them. My first site was Highway 79. This is a reverse curve. This was located northwest of Lincoln. The speed limits here were 60 miles per hour and vehicles were going on average 58 miles per hour. You have your given radius, super elevation of 5.2%, and the estimated friction utilized by drivers was 0.1. This is a video of how the vehicles go around these curves. And these are at 60 miles per hour. They're pretty tight curves as well. My second site was Nebraska 92. This one was in David City outside of Lincoln. This one, the posted speed limit was 60 miles per hour and vehicles were going on average 58 miles per hour. You have your given radius, super elevation of 6.9%, and your estimated friction utilized for this site was 0.01. And here's another video of vehicles going around the curve. My third site was Northwest 31st Street, and this was around the airport area, if any of you are familiar with it. The posted speed limit here was 45 miles per hour, and vehicles were going on average about 47 miles per hour. So they're going faster. That means they feel more comfortable going around this curve than the posted speed limit. You have a smaller radius of 944 feet, super elevation of 3.2%, and the estimated friction utilized by the drivers was 0.12. My last site was Northwest 40th Street and 1st Street. This is in Raymond. This one is a gravel road compared to the other ones that were paved roads. Here your posted speed limit is 50 miles per hour, but since it is a gravel road, you're going to go slower. So the average speed was 25 miles per hour for the site. You have a very small radius compared to the others, a super elevation of 3.2%, and your friction was 0.15. So going back to that maximum side friction from the Green Book of 2011, I'm going to compare it with not compare it, but I'm going to show it with my site. So the first site, which was Northwest 31st Street, you could see vehicles ranged from 5 miles per hour, nearly almost to 100 miles per hour, with that exception of one vehicle going pretty fast. You can't exactly compare it since these are dry pavements. They were not done on any wet pavements. The Green Book was wet pavement, so you can't exactly compare it, but you can see a relationship between this. Then you see down here how there's some negative values. So the reason for the negative values, we go back to that centripetal force. And for centripetal force, you have super elevation, gravity, and your friction. At low speeds, if your gravity is enough to keep that vehicle on the road, then your friction is going to work the opposite, and it's going to give you negative values. That just means that what's keeping the vehicle on the curb is the friction. Did I say that right? Yes. Okay, so now we have Highway 79, and you have vehicles ranging from about 30 miles per hour to no more than 80 miles per hour. There's Nebraska 92. You have them going about 8 miles per hour to also almost 100 miles per hour. and you also have these negative values. The reason why you have vehicles slowing down is because these are, again, at highway, railway grade crossings. You have big trucks that have to stop since they're transporting petroleum, chemicals, hazardous liquids that forces them to stop at these intersections. Then the last site was the Northwest 40th, which was a gravel one. We do have higher friction values here, but because it's a gravel, so you're producing more friction as you're going around the curve. My concluding remarks for my research, obviously more needs to be done. I need to get more data at night under different conditions like rain, ice, not just dry. And maybe, but not really, stay away from railway grade crossings, such a tongue twister to me, to see how vehicles react, but also, since I am looking at the safety in these crossings, look at different sites and see what vehicles are doing there. I want to give my acknowledgments to the Nebraska Transportation Center. Thank you, Dr. Rowlett, for having so much patience with me. I want to give thanks to Cody, the Nebraska Department of Roads, for giving such great information. The University Transportation Center for Railway Safety. I want to thank Cassandra and Anna, who were here this summer as interns, and they helped me with the data collection. Thank you.